Okay, today the plan is to go to solve the midterm questions in 50 minutes, okay? So you had 105 minutes in the exam, so let's see if you'll be able to solve it in 50 minutes today from scratch, all of them. So I'm going to go over all the questions, and also before we start, do you have any questions about the assignment? Maybe this would be a good time if you have questions with your assignment. I can also try to answer them. Yes? Extend the deadline? No. Unfortunately, we are on a very tight schedule. We are going to have the second part, and I'm going to have another assignment, so we will not have time for another assignment. So I'll think about it, okay? I'll think about it, whether it's possible. I'm going to look at the schedule and see whether it's possible to have a 2 or 3 day extension. Yes?
How many match states there in
Maximum number of match states?
approximately?
I mean, it's the maximum number of match states is the length of the alignment. All of them may be match states at the... Oh, okay. I mean, I'm not going to, your programs are not going to be tested with test cases other than the ones that I give you, okay? So you can, whatever the maximum length of the alignment in those 5 tests, I think there are 4 of them, right, in this case. There are four multiple sequence alignments. Your program is going to be tested on those 4 alignments only. We are not going to test it with other things, so just you can make assumption in terms of length. You can make assumptions based on those test cases. Any other questions? And there were some questions that was asked in the news group. So if you haven't been following the news group, you should definitely follow the news group to, for example, the determination of match. There was something wrong actually with the emission probabilities in the first, when I first posted the assignment, the example HMM output was incorrect in terms of emission probabilities. It was counting the gaps as well when in emission probabilities. But when we are thinking about emission probabilities, gaps should not be counted. However, in determination of match states, when we are the frequency, when we are computing the frequency of amino acid in a column, if there are gaps, those gaps should be counted when computing the frequencies in determination of a match state. After you determine that it's a match state, the emission probabilities should not count gaps. Okay, that frequency and emission probabilities are different. So that was the one thing that was updated in the. I mean the assignment specification, assignment document is not updated. There is no need for that. But the example HMM output is updated to account for this fact. Are there any questions about the assignments? Okay, so let's go ahead and solve the midterm questions. There were 3 of them. The first one is the semi-global alignment question. All right. Oops. I need to, can I zoom in the, anyway, I'm going to, so here's the question. So this is the partial scores table for a semi-global alignment. In semi-global alignments, the whole sequences are aligned. It's not a local alignment. So whole parts of the sequences are going to be aligned. The only difference is that if we have gaps, terminal gaps, similar to that flanking idea, but this is not, we don't have any flanking region here. If we have gaps that appear at the terminals, they are not panelized. And in other words, in the partial scores table, it means that the gap penalty is not going to be, we are not going to see the gap penalty in the first row and in the first column, and also in the last column and the last row, we can freely move from left to right without incurring any gap penalty, or we can freely move from top to bottom without having a gap penalty. Okay, that's because these, the last column, the first column, the first row, and the last row, they indicate terminal terminal gaps. They correspond to terminal gaps. Now, the question here is, so it says linear gap penalty is used, okay, and we have constant fixed match, mismatch scores for all types of amino acids. So we have a single match score, single mismatch score, and single gap penalty. It's linear gap penalty. And this is the matrix that is filled. And the score of the alignment here is 11, okay, because it's a semi-global alignment. It's not local alignment. Even though it was local alignment, still the maximum score is at this one, so or this one, either one of these two. But semi-global alignment, again, we need to look at this last cell, rightmost, bottommost cell, which gives us the score of the alignment. Now, part A, what is the match score, mismatch penalty, and gap penalty? So let's look at this matrix. First of all, we can, what we know is that gap mismatch and gaps are scored negative, okay? Mismatch penalty is some negative number. Gap penalty is also some negative number. We cannot get positive scores from mismatches or gaps. And therefore, actually, this cell here shows you your match score. Okay, that's, I mean, the first hint about your match score comes here. You have a match between these two amino acids, P and P. And what we have moved here, we got a score of 4. The score of 4 could have been got from the top, left, or the diagonal. But the top and left entries are both smaller than 4. Which means that since we have negative gap penalties, we cannot increase these numbers by adding the gap penalty, okay? I mean, these coming from left to this cell means that you can only decrease -2. If the gap penalty is 0, for example, it would stay at -2. Or if you come from top here, it would stay at 0, but it can never get to 4 unless the gap penalty is something positive. And the question says a gap penalty is not a positive number. You need to incur penalties. It's not a score. It's not a reward. So here, what we understand here is that we come from the diagonal, and this previous score here at this diagonal was 0. So the match of this P with another P is going to be 4. This is our match score. So our match score is 4. This is what we understand. Now, let's try to find out by analyzing this matrix the mismatch score, mismatch penalty, and gap penalty. Here, at this point, we have -2, okay? 0, 0, 0, -2. Now, we cannot tell anything by just looking at that cell. Why is that? Because both mismatch penalty and gap penalty both may be -2, okay? This cell itself does not tell you whether -2 is match score or gap penalty. It could have been both. So this, by looking at just -2, we cannot tell anything. So we need to look at other cells as well. So what we have, so here's something we have interest. So by going over all the cells, so let's try to see some interesting cells here. Oh, here, yeah, this cell is interesting. GP. And I have a 2 here, okay? This cell tells me, gives me a clue about gap penalty. Why is that? Why doesn't it tell me? Why? Because the match score was 4, so -2 to 2, it's 4. So match score was 4. It maybe tells something about match score, but no, because it's a mismatch, right? It's a G and a P, so it doesn't tell me anything about match score. Because G and P here, this cell entry is about G and P, so it doesn't tell me anything about match score. And mismatch penalty also cannot be positive. I cannot have mismatch penalty 4. So it means that, and also I cannot come from the left from -2 to 2. It's again +4. The only option that this 2 is produced is from this top cell, from 4. And what does it tell me? It tells me my gap penalty. Okay, so gap penalty, so matches 4, gap penalty is -2. So I have found 2 of these things. Now, let's try to continue analyzing this. For example, here it seems like an interesting cell. We have a mismatch, and however, this cell also does not give me any more information. So look at this 3 here, okay? 3 is surrounded by 6, 5, and 4. Here, however, this 3, since I already know that gap penalty is -2, this 3 could have been produced by coming from this 5 to 3, okay? So the only thing that this tells me is that mismatch penalty is some value mismatch penalty is less than or equal to -3. Okay, it can be -3, -4, -5, -6, -7. This cell only tells me that it cannot, for example, mismatch penalty cannot be -2. Okay, why it cannot be -2? Because if it was -2, I could have put 4 in this cell instead of 3. If mismatch penalty was -2, G and D mismatch, -2, 6 -2, it would be 4. I could put 4 there. So mismatch penalty cannot be -2. It's, this cell tells me it's something either -3 or maybe even worse than that. So I have chosen this gap penalty if it's worse than that. So this, I cannot determine the exact mismatch penalty by just looking at this cell. However, I just see an interesting, another 4 cells here, 7, 6, 7, 6, and 9, 6. Okay, since I knew my gap penalty was -2, I cannot have produced these 6 from those 7s. The left 7 and top 7 could not have produced this 6 because it would be 7 -1, 7 -1. I know my gap penalty is not -1, it's -2. So the only way that I could produce this 6 is coming from this diagonal. This is V, and it tells me my mismatch score is actually -3. Okay, so we are done with the first part of the question. So in your justification, you can write things like this. When I was explaining this, okay, this mismatch penalty cannot be this match penalty. Therefore, I need to come from this cell. So you just need to show in your justification how you found this -3. Which cell helped you in finding these numbers. You don't need to provide very long justifications. Just say that, okay, at this cell we can see we see 6 here. I know that gap penalty is -2, for example, so I cannot come from these cells. So it has to be from this, and which gives us the mismatch score of -3. Now, let's look at the part B. I have 3 parts, right? Yeah. So show a traceback of the optimum alignment on the table and also show the alignment below. So we are going to start with this, and I know my scores now. Since you know your scores, you can do a traceback easily after you know these scores. We are going to start with this rightmost entry, okay, which is 11. So from this rightmost entry, where are you going to go next? Can you go diagonal from 6 to 11? No, because your match score was 4. And although even your match score is 4, it's not a match. It's M and E, it's a mismatch. So the only place that you could have come is from the left, which is a terminal gap. So you don't incur any gap penalty. I mean, that seems like a trick first, because you can say, okay, it seems like this last cell, if it was global alignment, with these scores, it seems something is wrong here. The cell is filled incorrectly. but actually it is filled correctly because this gap here is not penalized because it's a terminal gap. Therefore, we don't have that gap penalty shown in that cell. So it's coming from this left cell, meaning that I have a gap against M. Okay, this is the first thing I do. I consumed M. I went to the left. I'm still at E here. I'm still at E. Therefore, I did not consume the last sequence here. Going left means that putting a gap against this M. And from here, since I know my gap penalty is -2, I cannot have come from left and top. So here it's a match from 7 to 11. So it's going to be, after this point, I'm going to be here at 7, meaning, and my alignment is going to consume both of these E's. And right now I'm at the 7. So 3 to 7 is possible if this was a match. However, V and D is a mismatch. So 3 to 7 is not possible, 1 to 7 is not possible, 9 to 7 is possible. So I'm going to have a gap against V. Now I'm at this 9, and this 9, you immediately see that you need to come from this diagonal. That's your only option, 5 to 9, which is match with a D match. And right now I'm at this 5. And this 5 again could only be produced with a G and a G match. If you look at the 3 neighbors, this 5, this is your only path back, okay? 1 to 5. These gaps is not possible to produce, they cannot produce this score of 5. So you go back 1 again. So what is that? Was a G and a G match. And then right now I'm at this 1. And again, this 1 could not have been produced by these top and left cells because I know my gap penalty is -2. It's not -1. So it's going to be a mismatch of G and an A. Actually, I see also that these 4 cells also gives me a clue about mismatch penalty. Instead of using this one here, 976, I could also use this one. So you can justify these results by using different cells. There is no unique answer to this question. You can use different justifications for this. So here we go from 1 to 4. Again, I have a single option, single choice. So it's a G and an A mismatch. A was here, G was here. Okay. And right now I'm at this 4, and this 4, this was our only option again. It's a P and a P match, like this. And I'm at this top row right now, and my only neighbor is my left neighbor. And I go left, putting a gap against this N. Okay, so this is your final alignment. The terminal gaps are this and this. They are not penalized. And you can just check the score. And we have shown the traceback on the pad, so this completes part B of the question. And we can check the score, whether it's actually 11. Okay, how many matches we have? 1, 2, 3, 4 matches. 4 times 4 is 16. I have 1 mismatch. 1 times -3, -3. And I have 1 non-terminal gap. And if you sum all these up, actually, do I have 1? Yeah, it was -2, it's not -1. Thank you for that. So it's going to be 11. Okay, so we also verified the score, and it's correct. Okay, so the table is filled in correctly. And here, actually, after you complete part B, okay, when you're completing part B, you simultaneously solve part C. Why is that? Because when we were doing traceback, did we have more than 1 options at any time when we were doing the traceback? No, we always knew which cell to follow. which means that there's only a single optimum answer to this. So you can, as a side effect of solving part B, you also solve part C. Just say there are only one optimum alignment, because when we were doing the traceback, we didn't have multiple options of choosing multiple cells. Okay. Although, again, this looks like a trick question, because this cell here, okay, 9676, sorry, not that one. We had something like, it was, where was it? It was, where we determined the mismatch of, this one. Yeah, look at these 4 cells, 6, 4, 5, 3. Actually, if we visited this tree somewhere along the optimum path, if we were at this tree, we would have 2 paths to follow. Either we could go this way to the left, because my gap penalty is -2, or to the diagonal. So we could have followed these 2 different paths if we had visited this tree. However, we never visited this tree during the traceback, so this path is not part of the optimum path. Okay, there may be multiple paths to follow in the table, but which are not part of the optimum alignment path. So therefore, what we have is that, all right, where's the, so the result is there are only one optimum alignment, and our justification is that we followed only, we had single options when we were doing the traceback. Okay, that's one sentence justification. Are there any questions in this first one, in the first question? No. So let's go to the second one. So this is the profile hidden Markov model, similar to your assignment. So we are given these multiple sequence. Let me zoom in more. And we are going to draw a hidden Markov model, profile hidden Markov model, similar to that structure below. First, the match states. First, we need to determine the number of match states. A column in the MSA is considered a match state. So let's read this. Okay. So a column in the MSA is considered a match state if the majority of the nucleotides in that column is a nucleotide of the same type. Okay, so it has to be counting all the gaps. We need to have a majority, and in this case, we have only 3 match states. This TTT, this GGGGG, and this AAAAA is our match state. No other columns satisfy this property, so we are going to have 3 match states in this example. This one, GGG, TTT, and all A, okay? Now, let's draw this hidden Markov model. Since we are going to have 3 match states, by looking at the structure, let's draw our hidden Markov model and determine the emission. The first easy thing is the emission probabilities. So 3 match states, M1, M2, M3, I have begin, I have and I have an insert state here. Let me name it I0. I have another insert state, insert state, insert state. And I am going to have delete states, 3 of them. Delete, delete, delete. And that's my structure. Let me draw the arcs. Okay, it's like this. From this delete to this delete. State, insert state. So it looks like this. And from this match, I can go to this delete. Right. And from the inserts, I can also go to deletes. And from here, I can go here. And I have these self loops. And we are going to see most of these arcs are not going to be needed anyway. So you don't need to draw it like this in your answer. Yeah, so it looks something like this. The first thing is that's easy to do, to determine the emission probabilities at match states. If you look at our alignment, in the first match state, it's all 100% T, okay, by not counting the gaps. So it's T 1.0. In the second one, we have all G's. It's going to be G 1.0. And in the last match state, I'm going to have A 1.0. So these match states, they're all fully conserved, only single type of analysis. Now, the thing we need to determine that's going to be the difficult part is the transition probabilities. How are we going to do the transition probability first? Here, since these are match states, I know that this column is my first match state. And whatever emitted before this first match column can only be emitted from this I0 state, okay? I1 is visited after M1. Okay, so if there's something emitted before first match state, it has to be emitted from I0. So all these things, okay, A, G, T, 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 G, A, C, they are going to be emitted by the I0 state. So let's look at, actually an easy way to answer this question is to do something like this. By going row by row, okay, and determine which sequence visit which states. This is also going to, this is like a hint to your assignment as well. It will be, if you do it this way, it's going to be much easier for you. So I'm going to write here for each sequence which states are visited. Okay, for the first sequence, what does it do, the first sequence? It visits I0, M1, M2, I2, M3, and I3, and end. Okay, starting from, this is begin, so let me write it clearly. So I'm going to have our end here, and I'm going to use this space to denote the states visited. So also, immediately when I'm writing this, I immediately also notice that each column in this alignment corresponds to a state in the hidden Markov model. In other words, I already know these T, 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 G, 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 and AAA are my match states. And any other thing in the alignment, any other column in the alignment, is going to be corresponding to an insert state. Okay? They're not going to, there's no column in the alignment that corresponds to a delete state. Because delete states are inside the match columns. If a sequence does not have a letter emitted inside the match column, that's when it visits delete state. Okay? All the other columns here, so the first column here is I0. I0, 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 match 1, match 2, I2, I2, match 3, and the rest is I3. So I can label each column of this alignment with either an insert state or as a match state, okay? And it's like this, it's going to start with I0, and after M1, if I have some columns which are not between two match states, M1 and M2, all the columns in the alignment are going to belong to I1 state, okay? So if this is M1, if this is M2, if I have any other columns in between, they are going to be emitted at the I1 state. Because after M1, I1 is going to be visited. These are going to be emitted, then M2 is going to be visited. So each column in this alignment corresponds to something. And actually, how many columns I have? So as I said, anything other than that comes before it, for example, any column that comes before M1 is going to be I0. after that, and you immediately see that there is no I1 state, right? I1 state, no sequence have emitted anything between these two match states, M1 and M2 are just immediately one after another, means that there is no sequence that visited an I1 state. Actually, we immediately see here that this I1 state is not going to be needed by these sequences. Right? Because there is no I1 state that is visited by any sequence. All the sequences, they either from M1 to M2, okay, or directly from I0 to M2, or directly from begin to I2. Sorry, they cannot go from begin to I2 directly. They visit a delete state. Any sequence who doesn't have anything emitted at M1 state has to visit delete 1 state. That's the only way a sequence can skip a match state. The way to skip a match state is to visit a delete state. That's what the purpose of delete states is. So now for these 5 sequences, I'm going to write out by processing them row by row, since I know what each column corresponds to in terms of states, I just go over these sequences. So A, G, T, G, G, T, A. I can immediately say which states that these letters correspond to. So A, G, they are I0 states. T is the match state. The second G is match state. GT is the I2 state. Last A is the M3 state, and I go to the end. Okay, so these are the sequences that these are the states the first sequence visits when it's emitting its letters, these A, G, T, T, G, A. Now, let's look at the second one. The second one, everybody is going to start from begin. Okay, every sequence has to start from begin. The second one, it's going to go I0, I0, and oops, there's no T at that match column, so it has to go to delete 1 state. So it goes to delete 1, and then match 2, and then 2 inserts 2 I2s, and then M3 and I3. It has the C is emitted from I3. Okay, so this is the second sequence. I0, I0, D1, M2, I2, I2, M3, I3, E. The third one, this is the longest sequence, is going to have 3 I0s after B. 3 I0s after B. Then I have M1, M2. And then I have 1 insert, M3, 3 inserts. 1 insert, M3, 3 I3s. Okay, these last TTT, all of them, it emitted 3 sequences TTT, all of them are emitted from this last insert state. Then I have the fourth sequence, it's B, I0, and then TG, M1, M2. ACA. A and C are insert states, I2, I2. And then the last A is M3 state, and I go directly to the end state after A. Now comes the last sequence after begin. I don't visit I0, I don't visit M1, M1 is skipped, so the only way you can do is from begin to go to delete 1. It goes to delete 1, begin, delete 1, then match 2. Then I emitted 2 letters. Those TT are from insert states 2, I2, I2. And then I have match 2, match 3, and then last T is from I3. Okay, so if you have this, you have all the transition probabilities actually here in that table. Okay, so how are you going to find the transition probabilities? Like this. Just start with the begin state. From the begin state, which states do you go? I0, 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 D1. So it's what? 0.8 I0, 0.2 D1, right? It's that simple. So it's going to be from the begin state, I go with 0.8%. Sorry, do I ever go to M1? No, no deletes, no state goes directly to M1. Okay, so this one actually be deleted. It's going to be 0 probability. There is no sequence here which goes from begin state to M1 directly. From begin states, 5 times I go to I0, 1 time I go to D1. So it's going to be, this arrow is going to be 0.8, this arrow is going to be 0.2. Okay, just count and find the frequencies, 0.8, 0.2. So I've done with outgoing arrows from B. Now let's look at outgoing arrows from I0. Again, all we are going to do is counting. From I0, what do I do? So 1 I0, 1 M1, 1 I0, 1 D1, I0, I0, M1, M1, and that's it. So let's now count. Let's count the I0s. I'm from I0 to I0 transition. 1, 2, 3, 4. 4 of them. Okay, 4 I0, I0 transitions. Let's count I0, M1 transitions. 1, 2, 3. Okay, 3 of them. I0 to M1. And I have just one left. The only transition left is from I0 to, and one of them, I0 to delete 1. Okay, and these are my outgoing arrows, all 3 outgoing arrows. I0 to I0 is going to be 4 over 8. It's going to be 0.5. Okay, the total of these transitions are 8. 4 of them goes to I0. It's going to be 0.5. I0 to M1, 3 divided by 8. You can just write 3 divided by 8 here. You don't need to write the decimal form, okay? And here, I0 to D1, it's 1 over 8. So it's 0.125. So this makes it 0.375. Okay, so I found my transition values for I0. Now, let's look at D1. Okay, from D1 you go to M2 or D2. Actually, when we see this, there is no D2, right? In our visited states, there is no D2 here. Is there a D2? No, everybody has visited M2. Also, everybody has visited M3 as well. These are full columns, full GGG, full AAA. So D3 and these 2 states are also not necessary. Your structure is going to be simplified because you don't need those states. The only state I have, delete state, is this. So the structure is going to look like this. And from D1, okay, I didn't have, so it's like from D1, the only arrow we have left is to M2, okay, after deleting those states. And that should be reflected in our sequences that are visited as well. I mean, we shouldn't have anything else from D1 because we have deleted those states. If you see D1 to something else, it means that there's some error. It's like we are debugging right now. Where is D1 visit? Actually, and D1 only appears in these 2 places, in the last sequence and in the second sequence. They are both to M2s. Okay, so since you don't need to actually even count, this is just for verification. 1.0. Because the only outgoing arrow from D1 was to M2, so that should be 1.0. Now, from M1 to M2, let's see M1 counts. M1 to M2, there is 1 here. There is no M1 to M2, M1 to M2, and that's it. So Also, also we don't need to count. When I see the structure, I see that the only outgoing arrow from M1 is again to M2. So if you have only one outgoing arrow, it means that your transition probability is going to be 1.0. Okay, now M2, I have something else. I have two outgoing arrows, so it means that sometimes I go from M2 to M3, sometimes M2 to I2. So here, let's count them. M2 to I2, 1, M2 to I2, 2, 3, 4, M2 to I2. So I don't have M2 to M3 transition. All of them, every sequence who visited M2 visited the second insert state. So it means that this arrow, although it's in the structure, it's never visited. There's no sequence which goes directly from M2 to M3. We can check that because there's this, after the GG column, there's a column full of amino acids. It means that everybody visited this insert state, okay? And so this is going to be 1.0. We have little left. Now let's count I2 transitions. We are going to count them 2 by 2. So I2 to I2, I2 to M3, I2 to I2, I2 to M3. Sorry, it should be I3, right? This one, there's something. Oh, no, we are in I2. Yeah, we are in I2. I2 to M3, I2 to I2, I2 to M3, I2 to I2, I2 to M3. It's like, let's count I2, I2 transitions. 1, 2, 3, 4. I2 to M3 transitions. 1, 2, 3, 4, and 5. Okay? It's going to be, this one is going to be 5 over 9, and this one is going to be 4 over 9. Okay, the self transition is going to be 4 over 9, the other is going to be 5 over 9. And we come to M3. From M3, this sequence goes to end, this sequence goes to I3, I3, I3. So 3 of them goes to, 3 over 5 of them goes to I3, 2 over 5 of them goes to the end state. Okay, these are the transitions outgoing from M3, and we go to the last one, I3 transition. Let's look at I3s. This one, I3 to end. So, and there are 2 outgoing arrows from I3, either to the end or to itself. So let's count the transitions to itself first. 1, 2, and that's it, right? 2, 2. Yeah, I have 2 to itself. And to the end, 1, 2, 3. So it's going to be 3 over 5 this, 2 over 5 this. Okay, there are 5 total transitions. So this completes the transition probabilities. We have the emission probabilities. So the final hidden Markov model looks like this. As you can see, what made us complete this quickly was having these, okay? Counting is much easier if you know which sequences have visited which states. Instead of processing the multiple sequence alignment column by column, I first processed it row by row. That was the hint in your assignment. Processing it row by row showed me which states are visited. And counting and processing them 2 by 2, you know which states you visit after which state. Okay? If you make these count, at the end you have your transition probabilities. And actually by writing these rows, we also simultaneously at the same time solve part B. Okay? Part B says that what are the sequence of states of HM that are visited to emit the sequence CTG-ACA. Which sequence was that? It was the 4th sequence. It shows here, begin I0, M1, M2, I2, I2, M3, E. Okay, and that's it. So this information is already in the alignment. So you just write these states for part B, and we have solved this question. Now, we come to the last question. This was an interesting question that it used Viterbi algorithm, but the Viterbi formulas are now different. It's not, we don't have match states, we don't have delete states, we don't have I0 states. So you need to write. This required you to understand what the Viterbi was actually doing. And our Viterbi equations are going to use only these 3 states, okay? Start, rainy, and sunny. And the table you are going to fill in is actually, you are going to fill in like 8 entries only. Only 8 entries in this table. So it's like we have 3 states and we have 4 symbols that are observed. Walk, shop, clean, walk. So 4 times 3 is 12. You are going to fill in a table of 12 entries. And the addition of empty symbol is going to be 15 entries. Okay, so we are going to fill in a table like this. So is it okay if I erase this? So I'm going to use only 5 minutes. I'm not going to solve because we ran out of time. We couldn't solve the last question fully, but I'm going to do it tomorrow. I'm just going to show how to solve the problem. So the Viterbi says that these are my states. So start, rainy, sunny, and I'm going to have the empty symbol, walk, shop, clean, walk, walk, shop, clean, walk, okay, it's 3 times 5, so 15 entries. Not 15 entries in this table. However, a lot of entries are going to be 0. For example, here, these are going to be 0. You cannot be at the start state and having observed some symbol, because these symbols are emitted at the rainy or sunny states. And this one is 1.0. At the beginning, by having emitted no symbol, you are at the start state. You cannot be at rainy or sunny states without having emitted nothing. These parts are also going to be 0. Okay? So 0.0, 0.0, which leaves you with how many cells to fill in? 8 cells. Okay? You need in this question, although there are 15 of them, 7 of them are filled with 1 or 0 easily. You need to fill in these 8 entries by using the Viterbi dynamic Viterbi recurrence relations. For example, how are we going to do that? Let's start with this one. What is this? This cell says that what is the probability? So that you are at the rainy state and you have just emitted W. This first W. Okay, it's this the first W. So it's either if I'm currently at rainy state and I have emitted this W just yet, I'm going to write it here. The emission probability of W from the rainy state, because if I'm currently at the rainy state and I just emitted W, I need this W is emitted at this rainy state. If you emitted this W, you are going to look at this max. Okay. Before the rainy state, which states could you have been? You could have been in all, because if you look at the incoming arcs to the rainy state, you could have been in the previous rainy state, previous sunny state, or at the start state. So we are going to compare these two things. V are empty, V sunny empty, and V start empty. And the transition, the respective transition probabilities from rainy to rainy, sunny to rainy, start to rainy. Okay? Start to rainy. Now, when filling in the first entry, you immediately see that, what are these values here? 0, right? So here our max only chooses this one. We start one, this is 1. What is the transition probability to rainy? It's 0.6. What is my emission probability of W at rainy? It's 0.1. So here it's going to be 0.06, okay? So the first table entry is filled in like this. We can fill in the second one similarly. What is the probability of being at sunny state W? Again, these two things are going to be 0 for when we are filling this max. The first two, VR empty, VS empty string is going to be 0. It's going to be the emission probability at sunny W times the transition from start to sunny. So it's going to be 0.4 times 0.6. It's going to be 0.24. Okay? And when filling in the remaining ones, we are going to, since I have run out of time, I'm going to stop here. I'm going to fill in just remember these two values tomorrow, 0.06 and 0.24. I'm going to fill in the remaining 6 entries tomorrow, okay? So see you tomorrow, and we are going to continue with the new subject after that.